Hello guys, welcome to our third session of Dive into Deep Learning. So today we will be going to cover a really interesting topic, which revolves around how can we model sequences essentially. So one of the most prominent method in deep learning era is recurrent neural networks, and we will try to first understand it in from theoretical perspective and then from coding perspective. First of all, here's the outline. So we are first going to cover what are sequential data, then look into some of the classical methods, and then we move on to the deep learning realm. And for it to work, of course, we need to do some preprocessing, uh, and then RNNs, GRU, Lstms, and so on and so forth. So sequential data, and where can we find them? So anything that changes state can be thought of as a sequential data. So for example, the video that we are going to be recording is in fact an example of sequential data. People are coming and going. This is also a sequential data. And me rambling is also a sequential data. And EEG data and some of the most formal data sets that we come across in practice are, of course, EEG data. Spread of virus is a really important concern, especially in these times. And of course, stock prices and derivatives. And we can also model earthquakes as well. I think we will look into it briefly. I think. And yeah, of course, it's short, it's everywhere. But how to model them essentially? So the classical way of modeling it is think of it as a stochastic process. Stochastic process is nothing but uh, it's distribution which is indexed by time essentially. So there are, I think the most famous stochastic process is Gaussian process, but in my left here, I'm not sure if you can see. Yeah, so yeah, I hope you can. So in my left, I have used, so these guys have used Hawk's processes in order to model COVID cases. There's also, of course, stochastic differential equations. The most famous one to model by virus spread, and most of the virologists came across when they start this study. And these methods are known as uh, SIR models, essentially. So you can look more deeper into it by just clicking into that link in the slides, essentially. Um, and so what other methods that helps us to model the sequential data uh, autoregressive models? So they kind of assume that, of course, you have a probability distribution which tells you what comes next given what have occurred earlier, right? So the autoregressive models assume that the distribution is going to be stationary. That is an important assumption. Uh, and secondly, of course, we in order to uh, save our sanity, I should say, so we are only considering the last tau states essentially, rather than going into the only the original state, which doesn't sound to be a good idea. uh, and another way to model is of course consider latent variables. So what are latent variables is, think of it like a hidden state, right? So what happens is that you can store a particular state which is hidden, of course, and which tells you that what components we can use from the past in order to give better idea or give better context to what is going to come next, essentially. So in short, you are summarizing all the relevant information about the past. Another method is Markov chains and Markov models. And in this case, usually we set tau equals to 1. So we are only considering whatever comes in the previous state in order to define what is going to come in the next one. Uh, Other advantages of this, that of course it's a foundation algorithm for Reinforcement learning, and of course, dynamic programming is heavily used in these scenarios. And last but not the least is Kalman filter. You can think of it as a probabilistic PCA, right? In continuous domain, right? And now with that gets out of with the way we can focus on what today's session is about mostly. So since we are following deep learning book, right? Dive into deep learning, right? So in order to use deep learning model, we first need to pre-process our data. One prominent step in pre-processing data in the case of a language, right? So we have a sentence, right? So this is a sentence. We can break into smaller chunks, right? We can break it into separate words. So this is also known as word tokenization. And you can, of course, take two words and of course, you can take two words, which will give you more context. You can also take three words, and these 1, 2, and 3 are also known as unigram, bigram, and trigrams. And of course, once we have tokenization, we can, in order to convert it into numbers, we are going to be using a process called vectorization, right? So which will convert it to vectors, and because we have vectors, now we can use optimization and of course train a neural networks in the end. I think, yeah, I think that covers it all. And stemming and limitization, this is another important pre-processing step. So in NLTK, we have a snowball stemmer and WordNet tokenizer, I think. So what stemming and limitization is, so it essentially takes a word and throughout all the irrelevant parts and only take a particular stem word, right, or a lemma. So as you can see, in adjustable gets converted into adjust because that is the main word uh, according to a particular function, right? A stem function or stemmer, right? And lemmatization, I think, is a bit more harsh than stemming. So usually people use stemming more than lemmatization. That has been my experience. And of course, we don't have to do any of course, instead of using classical vectorization techniques, like for example, TF-IDF can also be used as vectorization techniques. We can also use a neural network in order to learn those vectors. So the way to do that is train it in such a way that you wanted to uh, predict what is going to come at a particular location, given what has already been given to you in a particular context. Like for example, this is a sentence. So in order to predict a is in that particular sentence, the sentence and this is already been given to you as an input, and you wanted to predict uh, the word is, right? So by doing that procedure, what you end up with is embedding that is, of course, the weights of your neural networks, which you can use as a vector, right? So there are two ways to do that: continuous pair of words, and of course skipgram. Skipgrams use the other way around. I think you can. Okay, I will go deeper into it if there is any interest, but I'm just going to leave this for now. Now, our main part, recurrent neural networks. So this is what RNN looks like essentially. So think of it like deep neural networks, and you just flip it, right? And all of the hidden units are being shared. All of the weights are being shared. So here we will be using three different kind of weights. I will talk more about it as we move along. RNNs can be used in many contexts. We can use one-to-one, one-to-many, many-to-one, and many-to-many, and many-to-many. So these different architectures serve different purposes. Like for example, you can use sequence to sequence modeling, for example, in image translation. I will talk more about that as we move along. Essentially, we can also use different architectures to do classifications, and of course, intent classification is a really important part in practice. And I think uh, RNN, I think this is great for RNN. Yeah, of course, from mathematical point of view, what we have to do is essentially we have three weights, right? So one weight that is shared between inputs and your hidden state, and another one is between your output and the hidden state, and the weights which is being shared inside hidden state all along, right? Now, in order to update that, you need to, like for example, you have a word, right, and it turns up to be a wrong prediction. So what you essentially wanted to do is you wanted to punish all of the other hidden units and all of the other predictions because they are the reason why you made this wrong decision, right? So in order to do that in the backward pass, essentially, what you are doing is taking the derivative of it and back propagating it through time. Hence the name back propagation through time, BPTT in short. Right? RNNs can also be used for images, as you can see here. This image is taken from Andre Karpathy's blog. I've added the resources in the last section as well. So, of course, now let's talk about the problem with recurrent neural networks. So, as you can see, as we go deeper and deeper, and as we take into account more and more larger sentences, it turns out that the gradient vanishes. So, gradient when it gets back propagated won't get that far because, of course, you are taking the derivative of you are taking the derivative and scaling it, and of course using that, doing that recursively, which will vanish the gradient in its entirety. The way to fix that is LSTM, which we will cover in the next slide. But of course, to be more verbose, we have this problem of vanishing gradients. So the disadvantage of this problem, hence the reason it's called problem, right? So the disadvantage of that is, of course, you have a really long sentence, right? And you can't even remember what I said to you 5 minutes of 5 seconds earlier, right? Because you are forgetting it. So that is a really huge drawback in RNNs, which we'll see how can we tackle. The way to tackle it is to use different method. One of the most prominent one is long short-term memory. So this is what Lstms looks like. So this is an Lstm cell. So here we use the concept of gates. So what are gates? So essentially it's just a multiplication. It's a element wise multiplication, which says if I multiply a particular vector with 0, right? So of course that 0 that vector gets ruled out, right? So you can essentially forget that particular vector which is irrelevant to you in a particular context. Now in LSTMs we have three gates. One is input gate and forget gate and output gates, I think. Yeah. So it's not written here. I will add more context to it as we move along. And of course, here we are using previous cell state. So LSTM cell, we are using previous LSTM cells. We are using forget gate, as I mentioned earlier. We're using input gates and a candidate, and of course the new cell state will get move along for the next time step. Now here's the vanilla RNN, and here's the LSTM cell. If we look more deeper into LSTM cell, what we can see is essentially we have a conveyor belt, right? So the LSTM cell, the output of the LSTM cell in the previous time step gets injected to the current time step, right? And here we are essentially using 3 sigmoid layer output, which decide which information is to let through and which to rule out, right? So you can think of it as some information that you can forget and some information which is important for you to retain, right? And here we are using the input word, right? And the hidden state from our original uh, RNN neural networks, right? So the hidden state of our original RNN, we are taking both of them, concatenating them, and add activation function, which will tell us that should we forget the particular word or shouldn't, or we should retain it, right? Because here we are essentially multiplying it. But for now, we have only calculated the activation part. Stage two, of course, they are decide which state value to update and what values to update with, right? So it essentially tells you which word which is not there up till now, which we really wanted to be there, right? So we can tell our neural networks how to handle that situation using activation function and of course another activation function and multiplying it by that, multiplying both of them. And I think step 4 is to produce output with 10h and deciding the value and signal deciding the filter. So what we end up with is now we know which word to forget, now we know which word to add, and at the same time we essentially take all of the previous context, like we've taken all of the previous inputs of hidden state as well as the state of LSTM as well as the inputs, right? So using all of those information, we can essentially uh, uh, retain we can essentially ask what to retain into our memory and what to lose, right? So you can think of it as adding a memory in our neural networks, which is turned out to be an extremely important idea, especially in today's world, right? But of course, today we are crazy about attention, which is going to be the next session. But for this one, this is how are we going to prevent the catastrophic forgetting and as well as the vanishing rhythm. Now, there's another architecture, gated recurrent units. And the difference between LSTM and GRUs are GRUs has two gates, which is reset and update, and LSTM has input, output, and what to forget. And finally, there are other architectures which helps us to do certain tasks, right? Now, in RNN, in the forward pass of RNN, what we essentially are doing is only taking into account the previous words, right? Uh, but what if we also include the words that is going to come uh, after the current time step, right? So that this will eventually give us more context and eventually improves our prediction accuracy. Now, there is another important task, especially in current NLP landscape. It is called sequence to sequence, or I should say machine translation, right? So what essentially we wanted to do is we have a language, of course. For example, we have to convert from English to France, right? So we can do that using bidirectional RNN, but it's not going to work that well. So what researchers like Ilya Sutskever and Cho in 2014 has done is to give you a really nice framework which is known as encoder and decoder architecture. And what does essentially do is it calculates an encoder vector, right, using RNN layers, right? And using that encoder vector, we can take that encoder vector and put it inside another RNN network, which we are going to denote it as decoders, right? So it's going to take that vector and decode it into our desired language. So this part only deals with converting English to a vector, and this part deals with taking the vectors and converting into French or Japanese or so on and so forth. Although Japanese is extremely hard because they have a lot more words or a lot more letters, right, than English. Uh, and I think that's it from RNNs, and of course the more modern architecture that surrounds RNN essentially. If you wanted to read more about it, there's a really nice article by Article Pathi, and there's a really good visualization by Andreas in a distal article on RNNs, and there's also a derivation if you wanted to look what it is. And resources for NLP is our classical Stanford deep learning course, and there's also a really good resource that I like is by University of Alberta Linguistics and Computational Linguistics. Was a pretty old one, but it also deals with some of the classical methods like probabilistic graphical models and also Levenstein distance and things like that. And of course, anything Noam Chomsky has touched. So if you're really if you really wanted to go deeper into linguistics, I think this is a really important guy to follow, I guess. I'm not a linguist. Susanna is linguist, so she's probably cringing right now. And of course, from a time series perspective, MIT's Alan Oppenheim's course, it's a pretty old course. It's was I think created in 1990s, but it's still a really good course if you wanted to know the nooks and crannies of signal processing. And of course, you can use that idea in doing neural signal processing, which is good. And I think that's it from my side. If we have time for some questions that we can do, otherwise, I guess Pierre, it's your turn now.
Okay, thank you so much, Mrityunjay, for the nice presentation, and good evening, everyone. As it's written here, we will do now 60 minutes of coding, where we will code up the recurrent neural network, and we will also talk a little bit about the LSTM. So let me share maybe my screen with everyone. Continue. Here we go. You should be able to see my screen, right? Can you confirm? Okay, great, perfect. So I've already shared the link in the Slack channel if you're interested in coding along. And otherwise, I'm really just gonna talk about the code which is in the book. And due to time constraints, we will only re-implement the most important parts of the model itself. And if you have joined us in the past few sessions, then you probably already know the drill about the first few lines, because first we are going to install the, oh, I have too many active sessions. Okay, let me, sorry, see if I can, oh, strange. Okay, let me try to already change my, okay, my run type is already GPU for later, that is nice. But why? I can only, Let me try to connect here again. Sorry about that. I'm not sure why. All right, now it's working. Perfect. Sorry for that. So here what we are doing is first installing the official library of the book. It's just for convenience because there are certain methods and functionalities that we will use in this book. But if you're interested, you can always check out the code later on. I think it's pretty well explained. Here we're gonna import other important libraries that we need here. Collections, which is a standard library and contains also a lot of useful data structures. And one in particular, the counter class that we will be using during this session. Here we import Ray just for manipulating the text data later on. And here the random library, and then here the main part where we gonna import Torch, since we are going to use PyTorch to implement our model, as well as here math. And here we just gonna want to print with matplotlib, but since we're using a notebook, we recommend using this command here. And the first thing that we have to do with any machine learning project is to first have a data set. And here we're going to follow the book one to one because we're also going to use the time machine from H.G. Wells. So the first step will be to get the raw data. And this is exactly what is happening here in these first few lines. This is why I had to install this D2L library. It's because it gives us already the access to the data set later on. And then here we define a function called read time machine, where we will first download the data set. And while opening it, we will read the lines, and then we return the whole text as a list. And here I define the function. Here I will call the function. And if I run the script now, D2L is not defined. Yes, sorry, I should have run this, of course, first, importing my libraries. And then if I run this now, yes, perfect. So you see it will first download the dataset, and I can see that I have 3,221 lines of text. And the first few lines, so this is the first line, which is the title of the book, I guess. This is line number 11, since Python indexing starts at 0, and this is line 101. So far so good, but as Mrityunjay said during the presentation, we first need to pre-process the data because we cannot feed words per se to our language model. So what we have to do as a first step is to do what's called tokenization. And the idea is pretty simple. We will feed the lines to our function, and it will return a list of all the words it can find. So here, if I run this function, you see here we have the first line of our text, which was then tokenized by word, which is exactly what we want as a first step. And as you can see here, sometimes the lines are blank, but we will just ignore that for now. The next thing we have to do is to create the vocabulary. So we have all our words. We don't really know how many words we have or how frequent these words are. So it's worthwhile to do a little bit of analysis and look more into how the text itself is structured. So here we defined a function called count corpus, and it takes as an input these tokens. And then it will basically just return us the frequencies using this counter structure, this counter data class that I mentioned before. So you can see here, if that's a pretty neat functionality of Colab, if you're using Colab, is that once you hover over any class, it will look for the doc string. So here we can exactly see what this counter class is doing. And as it's written here, it's basically showing that it will count for us the frequencies of the past argument. So we create here our vocab class, which will have a lot of very useful functions. First, we have to initialize this class, of course, and we will pass the tokens, the minimum frequency. This will be used later in another function, as well as some tokens we might want to add, but which are not already in the text itself. And here we will we will use the method that we just defined above. Let me just run, yeah, I've run this, that's fine. Let me just run it so that we don't run in trouble again later. Here it will call this method here, count corpus. And from this counter, we can start to get the token frequencies. And we will create some plots later on to see what these frequencies exactly are. But we also will have to define a token when we encounter, we have to create a token for inputs which the model doesn't really know about. And for this, there is this specific token called UNK. And we will add it to the list of tokens. And then we create this list called unique tokens, which will just sum up all the unique tokens of our text. Sorry. And lastly, we also want to create so for each token, we will assign it an index so that we can have a numerical number instead of text, because in the end, as Mrityunjay has shown, is that we want to pass vectors to our model and not text data. So to do that, we just assign a specific index to each token. And how we assign it here is that the first token, as it's written here, the one with index 0 will be this unknown token. And then we assign the next token depending on the frequency with where so token number 1 will be the index 1 will be associated to the token with the highest frequency. And then we go from there on. And the frequencies decreases and the index increases. Here we have a convenient method to know how big our index vector will be. So we know how many indexes we have. And here we can retrieve the token. And here we have the method to change indices to tokens themselves, because we want to easily go from indices to tokens and vice versa. And here we are just creating now a vocab class using this class we just defined here, this vocab object, and we're going to print out the uh, first 10 index to token. And if I run it here, it should be running. Yes, so here we see that, as I mentioned earlier, the first token, the first index 0 is associated with this unknown token. And then, as we would probably guess, the most frequent words such as the, I, and of are associated to the next indices. And then here we have the words for example, The Time Machine by H.G. Wells. And below here we have the associated indices. So indeed, if you look here at D, which we know is the index 1, it returns the correct indices. I haven't checked all of them, but I'm pretty sure that this is correct. We can also just take another line here, so line 10. Then the words here will be twinkled and his usually pale face, and so on. And then we can see here what the associated indices are. And we can now summarize everything together. We don't really want to call these methods every time we start a new project. So it's very convenient to define a function which will do all of these processing steps for us. And this is exactly what this defload corpus time machine function does. So here it will first get the data set, it will create the tokens, create the vocabulary, and at the end it will return the corpus for us. Here um, we just create a corpus of characters instead of words because we are going to use character level RNN and not a word level RNN for this session specifically. And if I run now this function here, everything should be okay. And now I can see here that my corpus has 170,000 uh, tokens, unique tokens, as well as um, 28 um, unique, sorry, those are the total numbers of uh, tokens in the text, and 28 is the number of unique tokens. 28 because we are, as I mentioned earlier, using character level modeling. So they are the 24, 25 letters of the alphabet plus a few other ones. So to just quickly summarize what we have done so far, text, as you, my guess, is a very important representative of sequence data. There's a lot of research and industry interest in processing text data and extracting information from it. So having such a data set is not uncommon. And to feed the text data to our model, we, as we discussed, first have to tokenize the text. So cut everything either into a word level or character level, and then assign a unique index to each token. And as we have also seen is that we have to add this unknown token just for data that our model might not really be able to handle. Are there any questions maybe so far? I'm not sure in the chat or otherwise. I should maybe mention that if you want to ask a question, you don't have to, but this session is being recorded. So please just be aware that this session is being recorded. And if you ask a question, your voice also will be recorded. But are there any questions for the pre-processing part maybe? Let me have a look at the chat.
What are we trying to predict here?
Yeah,
What?
we are. Yeah, thank you. Sorry. Yeah, we're gonna get into that exactly in the next section. So here we are only, I only showed how to pre-process the data, and now I will lay the foundation of what the problem exactly is and what we're trying to predict. But if there are no other questions, I could go exactly to that. Okay, I think there is also no question in the chat.
There is a question that landed in my DMs, and maybe I can read it out if that's okay.
Sure.
And the question is if character level analysis is common. Typically, he would see this done either on a word level or on a sentence level.
Right. To be honest, I'm not an expert on text data itself. Maybe Susanna knows much more about it. I would say, let's say for text, if you wanted to analyze text such as papers, books, news, character level probably isn't used, but text data could also be, for example, DNA sequences. It could be amino acid sequences. So text data doesn't only come into word formatting, so to speak. Sorry for a lack of better wording. But there are some examples where there are no words, there are just characters. So this is just a convenient way to handle both cases neatly. But I'm not sure if Susanna, you wanted to add something.
Yeah, it very much depends on the text and on the task. So I would also say you see that, I think, in industry a lot less to do character level. But yeah, it's certainly possible. There's token level, subtoken level, and of course document level as well. Yeah, it very much depends. So there's no one answer to that. And a lot of experimentation is as usual. But yeah, I think the most common one would be probably on a token level. Yeah.
Yeah, thank you very much. Okay, I think with that, we can jump to the next section where we will exactly define the problem and what we are trying to predict. So what the language model basically is some model which would give us the probability of a certain sequence. And how we can model that is for each um, input, additional input, for having this specific sequence, it will be the multiplication of having a certain token given all the past tokens which have already been predicted. So here is a very neat example. Let's say we wanted to calculate the probability of having the sequence. Deep learning is fun. Then what we will need to calculate is the probability of having the first word, so deep, times the probability of having the word learning, given that we have already as the first token the word deep. And this continues. So for the third word, we need to calculate the probability of having the word is with the conditional that deep and learning have already been selected. And as you can see, this grows on and on. And we can already see that there is some issue if we wanted to model it exactly like this, because as the text is getting longer, we would have to calculate very difficult probabilities, and I'm not even sure it will be tractable. Probably, yeah, I don't want to say anything which is wrong, but even if we could, it would be a very, very difficult problem to solve. So this is not a very practical way to do the modeling itself. So instead of looking at all of the conditional probabilities, we can just restrict ourselves at looking at either the past or the past two or the past three tokens. And we kind of truncate how many tokens, previous tokens we want to consider. So here, for example, the first one, it's called the Unigram Model, or which has a Markov order of 0. For having the probability of this specific sequence, it will be the probability of the first, if this x1 times the probability of x2 times the probability of x3 times the probability of x4. But probably a model like this would lack generality. It doesn't really have any context, and it's difficult to say if such a model would actually perform well. So a better way, at least an improvement, would be to at least consider the previous token. And this is exactly what this second language model here would be doing. So this is the bigram model, which is Markov order 1. And here, for the first one, we don't have any previous token. So here we would just calculate the probability of having x1 times the probability of x2 given x1. And then here for x3, we will only consider x2 instead of x2 and x1. And here for x4, we only consider x3. And here for the trigram model, we will consider the past two ones. And for the first two terms, we don't have enough past data to have the full term, but for P where we try to calculate x3 and x4, we can do that. So there is some trade-off between simplicity and probably accuracy, or how much context we want to give our model. And if I'm not mistaken, we are going to use, I think we're going to see all three of them, but we might be using the Unigram model. So the first thing here, code-wise, that we are going to do is to tokenize again our text here. So here I'm just calling again my utility functions from before. And as it's written here, since each text line is not necessarily a sentence or a paragraph per se, we can just concatenate all of the text lines and just have one very long list of tokens. And then we can generate the vocabulary from this corpus or the text that we're trying to learn from. And if I run this, I should be able to see the token frequency. So this is very similar again to the ordering that we have seen previously. So D, I, and, of, A, to, was are pretty common in text, which we probably all would have guessed. And we can generate the frequencies of each token here. We're just going to make a list basically, which takes the frequency, so the second number here, for each entry in this list. And we're going to plot this later. And I'm here just going to do exactly the same thing again for the bigram and the trigram model. So here for the bigram, you can see that I'm always considering pairs of words which are adjacent to each other. So the most frequent one will be of the, in the, I had, I was, and the, and so on. If we look at trigrams, the most frequent one will be the time traveler, the time machine, the medical man, it seemed to, and there are other 3 tokens which frequently show up as a pair, in this case as a triplet. And the D2L library has a very convenient plot function. So we can, let me actually change the color here because it's dark and we won't see anything, but now, sorry if your eyes also got a bit hurt by this. But here, what we can see on this plot is the token index, as well as their frequency sorted. And what's really interesting to see is that it doesn't matter how we really count those pairings, whether or not we only count 1, 2, or 3 token. In the end, all of these will look exactly similar, and that's what's called Zipf's law. So what this law is on a very high level saying is that there will be certain words or pair of words which will appear with very high frequency, as we can see here, whereas most words will show up with low frequency count. And I should have pointed it out. These scales here are logarithmic, so it's much more pronounced than what we're actually seeing here. Here it's almost linear, but if we had used the unit scaling, I'm sorry, I'm not sure how to say it, but if we hadn't squashed it here like this, then what we will be seeing is just a big drop. Yeah, so this is a short introduction into Zipf's law. And now we're gonna talk a little bit. Let me just go back to doc here, since we're not using any plots. We're going to talk a little bit about how to feed the data to the model. So the first thing we have to do is to calculate the number of possible mini batches that we can. We talked about mini batches, I think, in a previous session. We cannot feed all of our data to our model directly. So what we have to do is create chunks of data, and each chunk will be passed to the model. And what we already can see here is that for a given mini batch size, there might be different ways to cut up our text. So here, for example, we decided to use 5-character mini batches. And this is one possible way to cut the sequence. This is another way. This is the third way, and so on. And basically, there is no right or wrong way of cutting it here. So what we are going to do is to just randomly sample one of these, because there shouldn't be any preference in how we pass the data to the model itself. So this is exactly what this sequence data iter random is doing. It will just create the corpus, get the whole text, then get the initial indices, then shuffle these initial indices, and then return the data. I'm not going to go into too much details of this code itself here, but let me just run it in case I need it later. And no, that should be fine. Here we're just going to see an example where we have a dummy sequence with 35 elements. And as you can see here, what we are feeding, or what we will be feeding to our model is here a mini batch of size 2 times 5, where we have sequence 9, 10, 11, 12, 13. And what we are trying to predict is the next character level. So here, since we have fed 9 at this position, the model should predict 10. Here we fed 10, so it should be 11. Here it's 11, so it should be 12, and so on. It's just that so nicely ordered because we are just feeding a sorted array here, but let's say in practice, it will be much more chaotic. It's just to basically demonstrate what we are feeding to our model and what the model is trying to predict. So to answer the question that was previously asked, we are trying to predict the same sequence, just shifted one to the right, basically. And I think I have an image in this notebook which shows that more nicely. There's another way to cut the data, and the idea is just that instead of having random starting indices, if I do it here, if the mini batch index here is 5, the code is just making sure, so here it goes up to 9, it just makes sure that on the next mini batch, the sequence will continue nicely. And same for here, so 19 to 23, so here it continues 24 to 28. And here we create a class just for having everything nicely wrapped up, and this will basically create the data loader for us, and it will this will be the thing which feeds the data to our model. So here I'm just going to initialize it, and let's talk a little bit again about the theory of recurrent neural networks. I'm just going to glance over it since we still have some things to do in this notebook. As Mrityunjay has shown, for this time step xt-1, we will be feeding the input character. Actually, you can see here M, for example. We are going to have a fully connected layer with activation function, which takes as an input this input xt-1 and the hidden state from the previous time step. It will calculate a new value. This value, or this new value, will actually be the hidden state of ht-1. It will be passed to the next time step, but it will also be used to generate the output of our model. So the output at each time step depends on this hidden state value here. And then at the next time step, we do exactly the same thing. Here we feed the next token. We take the previous hidden vector. We calculate a new hidden state, and then we get the new output from there. On a character level, this looks like this. So let's say we wanted to have a character level prediction for machine. Then here we feed M, and the model needs to predict A. We feed A, needs to predict C. We feed C, we need to predict H, and so on. And lastly, we need to talk a little bit about perplexity. This is just a way to calculate how good our model is doing. To be completely honest with you, I'm not very familiar with perplexity, so please bear with me on this part, and maybe we can come back to it during the Q&A part of this session during the last 30 minutes. But it's just, let's say that we calculate this metric using this formula. This is very close to cross entropy. Oh, sorry about that. This is very close to cross entropy. For each token, we calculate its probability. And historically speaking, people always have used perplexity, which is the negative of this value times the exponent. And we can distinguish three corner cases for this formula. There's the best case. So that is if the model predicts all the labels correctly, then the perplexity will be equal to 1. The worst case is if the probability of the label token is 0. In this case, the perplexity becomes infinite. And there is a baseline. So if the model predicts equal probability for all tokens, it hasn't really learned anything. But then the perplexity will be equal to the number of unique tokens. And this constitutes a very nice baseline that any model that we create should be able to beat, because otherwise it means that the model is not doing better than random. And finally, here in this section, we will now actually start the coding. That's why you can see all the to be filled parts here. So first, let's define our batch size and number of steps. So it's 32 and 35. Here we create the train iterator and the vocabulary from the method that we have already seen several times now. And the first thing we have to do is to define our parameters. So here, what I need to fill in, first the number of inputs is equal to num outputs equal to vocab size. So what we're saying here is that the number of inputs and the number of outputs has to be the same as the vocab size, which is making sense since we don't want to predict anything outside of the vocabulary. And then we're just gonna define here to shape. Here we're just gonna initialize. We're gonna initialize some parameters, and we are going to scale it here. And let's start with the hidden layer parameters. So here we're gonna have vxh which will use the which will multiply the input x. So here we're gonna call this normal function, and we're gonna have number of inputs, no hidden, and we are going to have exactly the same weights, but this time for the hidden state. And I think this here, of course, it has to be non-hidden since it's going to multiply the hidden state, and we're going to add some bias here. And this bias is just gonna be zeros for now. And we want to put it on the correct device. Next, we are going to define the output layer. And here I'm going to have Q. So this is basically going to take the value we have calculated previously, as we're going to see later. And this will create the output for us. Some hidden and some outputs. So here, as we can see, the dimensions match up. And as I said, we're going to take the the calculated new hidden representation, and we're going to cast it to the number of desired outputs. But we also want to add some bias to that. So we're going to add here torch 0, and the size should be num outputs, and we're going to put it on the correct device as well. And we also wanted to what's called attach gradients, because the tensors themselves won't keep track of the gradients themselves. So we have to make sure that we are adding this bit as well. HQ, BQ, and then for each param in params. So in all of my parameters, I want to set that param requires gradient. Okay, doesn't want to suggest that, but I'm going to set this to true. So this is just PyTorch's way to say that we want to keep track of these parameters. And if I run this, is everything going to be okay? I think so far so good. Let me also run this. Okay, perfect. Here, we also need to initialize the state of the recurrent neural network, and we are just gonna return a 0 tensor here, because we don't want to start with anything basically. And then let's define the model itself. So here our RNN will take the inputs, the state, and the parameters. And the first thing we are going to do is to unpack the parameters. So we're gonna assign them to these values here. So each one is named, and then we say that H, so our hidden state is equal to the past state. Oh, okay, nice. And our output so far will be just an empty list. And then for all the X in the inputs that we passed, what we want to do is calculate the new hidden state using torch. So here I'm going a little bit backwards because I know that my activation layer is going to be the 10H. But what we're going to do is torch, we're going to multiply the input with the correct weights here, plus torch. Here we're going to multiply the hidden representation with the correct weights here, and we're going to add the bias that we also initialized. So this function here, or this line here, will just calculate the new hidden state, the updated hidden state for us. But we also want to calculate the output. So to do so, we will do the matrix multiplication from this new hidden state with the correct parameters, which in this case is W, HQ, and BQ. And we're gonna append this new Y to our list to just keep track of what our model has been predicting. And finally, we are gonna return that. Here I'm gonna concatenate all my outputs so that it's one nice tensor. And I'm gonna return the hidden state as well. And let's see if everything, okay, so far so good. And lastly, what needs to be filled is the Rnn model itself, which will use this Rnn layer. So here what we did is just implement one part here, but we need to define the whole model itself. So if I come back here, we first gonna initialize our class, take self, vocab size, it will take the number of hidden we want, the device, of course, the parameters that we want to initialize, the initial state, as well as the forward function. And then we are gonna set the self.vocab size. Let me also set the self. distance equal to size as well as so I'm just initializing here these attributes so that I can keep track of them later on. And then for the parameters, I'm going to use the function that we defined here, just initialize these parameters with get params. And I know that what I need to feed to that is the vocab size, as well as the number of hidden that we want, as well as the device. And lastly, we need to initialize the state of our model and set the self forward function. And this will be equal to init state and forward function. Okay. Now, every time this class gets called, so we're going to have here self, it will have the input and the state. Here, I'm going to define what is happening with this input data. And the first thing we're going to do, we didn't really talk about it, but we don't want to pass the indices. But what we want to pass is the one-hot encoding of these indices. And what it will create is one vector with the vocabulary size where everything is 0 except for the index that I passed. So imagine that if I wanted to one-hot encode the index 2, then I would have a long vector of zeros except for this index 2 where I will have a 1. This is just to create a more useful representation of our data for the model. And here I'm just creating this one-hot encoding, basically. Vocab size. And here we're gonna set the type to float 32 because we don't need to have higher precision. And then finally, I want to return that function. I'm just going to pass the one-hot encoded inputs and the state, as well as the current parameters of my model. And finally, we're going to define here this begin state, which will call the init state function. So begin state self batch size and the device return self state. Lowercase here. We're going to pass all these arguments to that function. And the device I want to have my parameters on. And so far, everything seems good. And now here, I'm just going to use the utility functions of the book. So then there won't be much of coding. Here, probably, I think it's just to check if that model is working well. And let's see if everything is okay. Okay, I might have some issue init Rnn state. Did I forget to? Maybe here. I think this is the culprit here. No. No. Sorry, what's the error?
Your bias variable.
The bias?
Yeah. So you did leave it as b underscore.
Yeah. Can you?
Yeah. So go up, go up, go up.
Go up.
Yeah, just in this cell exactly. So in hidden layers.
Right. Thank you. Awesome. Yes, exactly. Thank you so much.
Yeah. Thanks, Ramesh. And
yeah. Okay, let me just rerun all of this to make sure that everything's fine. It says not enough Lstm pack expected to got one. But I'm pretty sure the state here, there is some issue. Here. Returning H. Yeah, it's complaining about here Rnn state. Let me just quickly check with my to go to maybe with my begin state. No, that's wait, no. This is also correct. Yeah, that happens sometimes during the preparation and during live coding. Yeah, there's probably some error. Let me just open the normal notebook with all of the code, which I know is running. We're running a little bit of time, so let me just try to connect here. Okay, you don't want to let me do it. Okay, let me manage my sessions. And okay, let's terminate other sessions. Okay, let me just run this whole script here. Now it should be able to connect. Yes, perfect. And here I'm just gonna run out. It has to download everything again. Sorry if it takes a little bit of time to collect everything, but I think it's actually already where I want it to be. So yeah, here we were defining this class Rnn model from scratch. And here we're using some code to test out. And as you can see here, we create the state by, or we first create the network by calling this Rnn model. And then we define our initial state and we pass this initial state as well as the input to our model, and we get the output as well as the new state. And if we check the shape here, everything is correct. And we're gonna define here another utility function which will create predictions for us. And if I run it here, I'm already running it, that's why it's a bit complaining. But you can see that if I passed here time traveler to this function, it would have the first part, which is correct since it's the input itself, and then some nonsense character level output. And one thing that the notebook did is implementing gradient clipping. So we don't want to have gradients which explode, and to do so what we do is to clip them. So we just allow them to have a certain norm, and if they're bigger than that, we just reduce it to that specific value that we can choose here. That will be that theta. So this is just making sure that our gradients are not running away. And this is also another utility function in which we would train our model for one epoch. So it's gonna keep track of the metrics, it's gonna keep track of the state, it's gonna calculate the output for us, and so on. Here is the main training loop where we call this previous function, and it will basically plot out everything for us. And if I show you this experiment here, let me switch again here to the light notebook so that we can see what's happening. What we did is to calculate the perplexity that I have shown. So the best value here is 1, and indeed our model achieved that value. And we can see that it was able to generate over 100,000 tokens per second using the GPU. And here we can see the predictions. If we pass in the sequence time traveler and the sequence if we pass the word traveler here. There is a more concise implementation. So what I've done previously was to create the Rnn from scratch, defining all the parameters and so forth. But high-level APIs really take care of that for you. So there's no need to do that. And this is exactly what this class function here does. Although it doesn't look more concise, it should be, because here we don't need all those functions that I coded out. We can just call here where was it? Here the Rnn layer. Here is just nn.rnn, and PyTorch will take care of the rest for us. If we run this experiment here as well, we can see that the model isn't predicting anything really useful because it's not trained. But once trained here, the perplexity also reaches almost 1. And what's really interesting to see is that the number of tokens has considerably increased. So there are some under the hood optimizations that high-level API will take care for us. And that can really increase the training speed if we don't use our uh, own parameters and own methods, but use things which are really optimized for in many ways, actually. So here we can see also the prediction. Yeah, obviously to the first model, the predictions aren't as nice. So sometimes the words aren't coherent. That's why I probably didn't get the perplexity of 1. But otherwise it's still not gibberish, so that's nice. And in the last 10 minutes that we have for this coding part, we can talk a little bit about LSTMs, because they have been quite widely used a few years ago, still are being used, although they are being replaced by transformers, because transformers have certain advantages that we will talk about in the next few sessions. The next 2 sessions will actually be about the attention mechanism, which transformers heavily use. So I will leave this for the next 2 sessions. But for now, we can have a look at the LSTM itself. And maybe just to quickly go over again what Mrityunjay was saying during the theory part. The most important part is the memory in the LSTM, because it's what carries or what helps us keep track of long range interactions. And there are 3 important gates. So the forget gate, the input gate, and the output gate. And the first thing which happens in an LSTM is that the hidden state and the input are first concatenated, and they are passed to the forget gate. And as you can see here, there is a sigmoid as an activation function, and the output will be either 0 or 1 because of that. Or sorry, it will be between 0 and 1. And here we do an element-wise multiplication of this value between 0 and 1 with the memory. And what this means is that here ht-1 and xt1 really choose or affect whether or not this these values here in memory will be kept or forgotten. So let's imagine that all the values here would be set to 0, then it doesn't matter what this ct-1 really is, because through this multiplication here, the memory will be wiped clean. And this is one important ingredient of RNNs, or the memory part of RNNs, is that we should be able to write new values to the memory, but also forget things which are currently in memory. So this takes care of the forgetting part of the whole process. The next thing is, well, we have a memory value here, which was either forgotten or not, but we need to propose a new value here. So this input xt and ht-1 will be passed through this fully connected layer with a 10h activation. So here the output will be between -1 and 1. But this input gate will also choose, or it will modulate how much of that that new candidate memory we really want to use. It could be that here the output of the sigmoid is close to 0, and in this case here, it doesn't matter what this CT tilde is because it wouldn't be added here to the memory anyway. So the input gate tells us how much of this candidate memory should leak to the memory itself. And once it's been calculated, we add it up here with the values from the which were calculated here. And this will be our new cell state. And this cell state is then passed through the um, tan h again. So the values will be again between -1 and 1. And here they will be modulated by the output gate. So again, it's a very similar story here. ht-1 and xt will be passed to this fully connected layer with sigmoid activation. And this will tell us how to create the new hidden state of our LSTM. So this is the overview of how the LSTM is working. I haven't written out the full model from scratch. It will take too much time, and we don't really have that. But just to have a look here, if I run this, PyTorch has a very neat function, nn.lstm, which will generate the LSTM layers for us. So here we just need to tell to this PyTorch function how big our input is and how big the dimension of our hidden representation should be. And then we can pass this forward function to our Rnn model, which takes care of the rest. And if we train this model here, you will see that we also reach perplexity of 1. However, here it's 4 times faster than our Scratch model, which is really, really nice. And if we look at the predictions are quite good, and it's not gibberish. Yeah, maybe it's also important to maybe say that uh, LSTMs really helped to avoid the issues of the long range interactions, so to speak. So if tokens are far from each other, it's difficult on a sequence model to really feel or to really create the relationship between these two tokens. And LSTMs are one way to keep track um, of these influences, even if there is a long range. And the LSTM is also neat at avoiding the vanishing and exploding gradients because everything here is either a sigmoid or a tan H activation function. So everything should be nicely behaved. Yeah, that's basically it for the coding part.